Just that because the website launched and the courses started, right? So I'm like busy with the courses. So let me just give a brief intro of what we are doing right now. So if you go to our website right now, the link is given in the description box. All you need to do is go to the website. Net is terribly slow today, sorry. So you go to my website and you go to the store, you find the courses out there. So right now we have this free Python accelerated course. So if you are into learning Python, if you don't know anything about Python, this is free only. So just come here and visit this and just start with the batches. We already have 50 students enrolled over there. It's free and we convert lots of quizzes. We have a Discord server out there. So go and check out over there. It's not just me, all the people of various different domains of Python sharing their knowledge. We hold a seminar every time with industry professionals. This is a huge thing that is going on, and it's not happening in YouTube. It's a YouTube continuation thing, right? So, in case you don't know anything about Python, you want to start from scratch, go and start with that. In case you want to know about machine learning thing, there's a course we also have for machine learning in detail where we talk about unsupervised machine learning, RASA, NLTK formats, and a lot more than that. It's the complete Python course, okay? And it's currently at a very low price compared to what we are offering over here. You can see what we are offering, right? It's huge. So definitely check this out and buy it if you want to. Now, what I thought is that there are some things that I, in general, want the community to know. There are some things that, in general, I want the community to know, and I would share them. So I thought that for supervised machine learning, for supervised ML, there are two methods, right? Two very popular ones: linear regression and logistic regression. Now, people don't seem to get the very differences or the real test case scenarios, the real way how to use linear regression. Like linear regression is so simple, yet that's why extracting the correct output from logistic regression or linear regression is a bit of tricky, like most tricky for linear regression. As linear regression not in does not involve only like basic ML commands. No, it's not blind ML command lines. It's more of applying data science the right way. Okay, using your knowledge of data science the right way is very important if you are into learning linear regression. So what I thought is I take a practical example of a very common thing that if you've learned linear regression somewhere, so you must have known about this small data set. It's called the real life example. I've named it. It's actually about car model prediction and the mileage prediction. All that things are there. So I will tell you exactly how I would perform a linear regression if I were in your place. I will share my thought process today. And if you do like the video, go and subscribe to the channel. I'm going to complete supervised learning, and for unsupervised learning you'll have to go and purchase the course. There we will continue unsupervised learning. I'm launching a course in Divine Academy for unsupervised learning only, and supervised learning will be covered in YouTube. Okay, so I try to make this interesting for you. So first, let's forget about linear regression. Let's see what data we have, right? So once you get this, you can see what things are given already, right? So we have brand, we have price of the brand, name, then the mileage, then engine type. All right, then we have registration, the year of registration, the model number. It's pretty cool, huh? Great. So what I'm going to do is, let me name it a car evaluation. Okay, let me name it car evaluation. I'm going to, I don't want to see anything, right? So this is somewhere in my desktop. Right, car evaluation should be in my desktop. I'll just locate it somewhere here. Live example. Where did it go? So in documents, yeah, somewhere here. Okay, yeah, we have real life example over here. So let me just take this thing to desktop because there's a lot of things over there. I don't want to mess it up. So I'll name it evaluation. Okay, bring buzzing. What did I just name it? So I'll name it car set. Basically car set. So I'm keeping the name simple. Okay, Now I'm going to use Jupyter Notebook. Okay, so before we start, how much do you know about logistic regression? That's the thing. So if I really open Google and I type linear regression, okay, if I type linear regression, you're gonna find a lot about linear regression, right? There is that formula of linear regression that you may or may not know, because I've seen people blindly copy the code. So linear regression's formula that you see over here, y equals to b0 plus b1x, this is basically an expansion formula. Okay, so basically y is what, if you see, let me change the color, this color is very ugly. Yeah, better. This is looking good now. I don't like purple. Okay, let's go with black only. Yeah. So y equals to basically b0 plus b1x1 plus b2x2 plus, like, in the end it comes to a bn, and basically x power 0, something like that. Okay, so x gets cancelled. So it's basically an integral type formula. Okay, if I really try to break it into integration, so it's basically the summation of the b constant from I equals to 1 to I equals to x. Okay, so from 1 to x it's basically going with an integration from 1 till x for the expression of x dx plus the slope. Now this basically means what? That if you draw a graph like this, so in linear regression you all know that we get a scatter plot, right? We get scatter plot, data scattered here and there. But there is a line of ascent like this regression line, we call it, right? We call it the regression line, and it's drawn along this edge from here. This is the x-axis, this is the y-axis. Now y-axis stores the dependent values, the dependent values, and x-axis stores the independent values, right? Now our target is usually to calculate something on y-axis, and for this x we have a set of data, sometimes set of data or an individual data, basically set of data. So linear regression basically involves two types. One is simple linear regression and the other is multiple linear regression. So we are focusing on multiple linear regression because for x we have a set of values. We are not making x have just one set of values. Okay, so we are having multiple values for x and we're going to calculate that y accordingly. All right. So for this car evaluation module and all, which car set makes the most of it? So can you actually guess what we are going to predict in the end? Any ideas? Well, actually, it's very simple. Like, you are going to see the model name and see the check the mileage and all. So ultimately, it's about the buyer. We're going to give a statistical inference to the buyer that which car is going to be the best and which not. So let's go ahead. Create. First, we need to upload that CSV file. Let's go and upload card set. We have card set uploaded. Now let's create a new Python file. We're using a low spec PC, not an issue because linear regression will run just fine on low spec PCs. So I'll just name it car evaluation project. Okay. Let me just give it a heading of practical example car evaluation project. Looks good to me. So first we need to import the libraries, right? So let's import the libraries. The first library that we're going to import is import numpy as np. So np is basically an alias we are giving to numpy. These are all the basic stuff. I am not going to cover that. because this is kind of an intermediate tutorial. You can get the idea that these are just packages. If you know Python, it's going to be like, even if you just know Python, it's just going to be fine. We just need the statsmodel.api, statsmodels.api, I guess. Okay, we're gonna see. So I'm gonna name it as sm import matplotlib dot pyplot. Just need just pyplot. Name it as plt, and we're going to import cborn as sns. C1 doesn't really do anything; it just beautifies the matplotlib plots. Okay, over here, it actually does a lot more than that. We'll go over that later on. sklearn dot linear underscore model. Now, for those who are more familiar with JavaScript, for them this underscore concept really doesn't work. There will be a lot of underscore commands for machine learning. Okay. So I'm just setting up SNS model for the pyplot. Just gonna import them. Now, if you do not have all these packages, you're going to have to install that. So for that, you can do it right here only. You can say pip install pandas matplotlib numpy cborn and linear regression, and just press shift enter. It would just do it. Okay, just a piece of cake. Just press shift enter after this, it will be done. Okay, so let's move forward. Now we need to load the raw data. Okay, so let's give this the heading of loading the raw data. So we're going to load the raw data. So let's name a file. Raw data will be the variable where I'm going to read this. Read underscore csv. Okay. So what was the name of that file we had over there? It was, if I'm not wrong, card set. Okay, card set. Okay, let's read card set. We're going to take quotes, name cardset.csv. Okay. So once you read it, I just don't want to read it. I just want to print the first 5 values, right? So this is very common, right? Dot data dot head, that will give me the first 5 values. But what I do is I don't take the first 5 values. I prefer to see the first 10 values. Now that's very unnatural of me, but I prefer to see the first 10 values, and I'll just show you why. Okay, so now that we have the data frame, now first see the trend in the first 5 values and then see the second, 6th value. So usually the discrepancies that occur in between these value sets happen between 0 to 9. So all the missing values, the problems and all that you may get visualized later on, they happen to be within the first 10 values. So seeing the first 10 values helps me, like, as better. So now what we're going to do, I'm going to give another heading, because now I'm going to do a very important thing that is very much needed over here, that is pre-processing. So I'm going to pre-process the data. So I'm going to do that. I'm just going to write raw underscore data, that's the name of the variable, describe, and I'm going to write include equals to all. So what does this all do? This is a magic thing. Okay, this is a magic thing. Now describe stats is a very useful for initial exploration of the variables. Okay, so for initially exploring the variables and seeing the problems they have, this describe thing is very helpful. But there's a small thing to note, that categorical variables don't have the same numerical descriptives. You can say categorical, let me just give it as a comment. categorical variables do not have the same type of numerical descriptives, same type of numerical descriptives. And don't worry, there will be a lot of comments in the Python notebook that you will get in the description box to, see through. I'll put all the comments that can be. I'll take time and think and then write the comments in this file and then give them to you. Okay, so now we have a lot of thing over here. Look at this NN values. Okay, not good, right? It's not good. So we need to drop a few things. Now let's go to model over here. Okay, so this model thing, can you see? Descriptives about model. I don't think this thing is really like helping. So let's do one thing. I'm going to drop model. Okay, I'm going to drop. Let's say write data, like raw data dot drop. What can I drop? I'm going to drop model. Okay, and I'm going to move it to the axis equals to 1. So now if I describe this data dot describe include equals to all. Okay, now let's see over here. Now let's deal with this missing values. Okay, so how to see the missing values? So basically you can say data dot is null, right? You can say data dot is null, but that will show me the null values. Now how many null values are present for each? Like you cannot remove data just like that. Okay, so it says that should lie between the amount of data you're removing. If the removal is from 5%, like 2% to 5% of data is removed, it doesn't harm the model's accuracy. It doesn't harm the model's accuracy. So let's do one thing. We are going to see the sum of the null data. Okay, now this magic command will show me the sum of the null data. Oh my god. Okay, some guys need to seriously be removed, right? Some guys seriously need to be removed. So let's drop the missing values. So let's drop the missing values. So I'm going to drop the missing values now. So how we do that? So let me just take another frame. Now see, these data frames now are immutable, so you cannot mutate on the data frames like this. So we need new variables every time. We need new variables when we have to drop something. Data dot drop in it, and we have axis equals to 0, right? We have axis equal to 0. Now let's check the descriptives. Let's check the descriptives. So what can you do? We need to describe this thing after dropping that. So what we are exactly doing? We are just dropping things, right? We are dropping things. Alright, so we did check the descriptives. Now I guess there are a few things that I thought I should have written it before. Let's see. So I want to write that by default only descriptives for the numerical values are shown. Right? So what does this mean? So the description of the numerical values are shown. This means that the mathematical aspect of the numerical values are kind of obscured, and so they do not reflect themselves like that. When you write this dot describe method, it kind of gives an estimation of the values for this 25%, 50%, and 75%. A sum of values is displayed for all the categorical axes, And this gives us a brief idea about what we need to separate and segregate for the X train set and the Y train set, right? So even without that, a small mathematical estimation is good enough to calculate or kind of give an analysis on where it should go. So there's another way by which you can do this, and that is you should specify this with an argument. You should specify this descriptive with an argument. All right, let's describe it. And now for after the description, let me just write the findings over here. So you can see that, oh, my bad. Note that right. So this is pretty self-explanatory what I wrote over here. Let's move on to the next thing. Now what I'm going to do is that after I'm done with this raw data description, okay, is null is there, we are done with it. We have dropped model. We have dropped model at axis 1 and we made a description. We have removed the null values. Now the most important part comes up is that we are going to explore the PDF thing, this is probability density function. So data when we describe, let me just include equals to all. All right, this gives a better insight to me. Okay, this is the point from where we are going to explore the probability density functions. So let me just give it a heading. So we're going to explore the PDF. Now for those who are not aware of what is PDF, so let me just come to my board. By the way, I'm using this Miro whiteboard app thing, and this is the official sponsor of this video and also sponsor of Divine Academy. So I'll just give a link of this in the description. It's free to use and it's got a premium plan as well. I also provide you with a coupon code that can give you a discount, okay, on the premium plans. So I don't think you would personally need this premium plans. Okay. Okay. So PDF says that if you have a graph like this, something like this, and this part is colored, okay, this colored part is basically the probability. This colored part is the probability of say E by A. Or basically the colored part is what? It's basically the area of this area of yes zones, the true zones, right? So or yes zones, whatever way you call them. So PDF can help us to visualize the trend of data. So let me just write, it's a great step in data exploration. Okay, the PDF variable is distributed. This shows how a particular variable is distributed. And this most important point, this makes it easy to identify the anomalies such as the outliers. And most importantly, again, this PDF is often the basis on which we decide whether we want to transform a feature. Now, I wrote so many points. Now we want to transform a feature, and then we talked about anomalies. So let's discuss these points. Now suppose you have a graph something like this, and this value is getting constant, and all of a sudden this goes like this. This is the zone of anomaly. Okay, this is the A zone, as I call it, the anomaly zone, because this is the data that is abnormal, the abnormal trend of data over here, right? So this trend of data over here is abnormal. So what we want right now is that we remove this data or transform this data. So maybe this small segregation of data, if the graph is reversed, okay, it's just for visualization purpose. So if this opposite trend is observed, then maybe this is actually making sense. So we need to decide whether we want to remove this data or we want to compare this y-axis with some other value of x-axis. So what we're going to do, say x has n number of parameters. Okay, n number of parameters. So we have x of model, we have x of engine, and so many things. So we are going to segregate each of them. We are going to segregate them and compare. Compare what? Their PDFs, probability density functions. This is a D. So let's go ahead and do this thing. So we can do what? We can make a dist plot, okay, for density, or probability density rather. So we are going to it SNS dist plot, okay, and we are going to use that former segregated data no underscore mv, and I'm going to do it for price, the most important factor, not out of only typical Indian mentality but of typically like from every country. Price is the thing that you always look at. Okay, this is giving a feature warning because it's saying that, okay, we just ignore the feature warning. If you write dist plot, it will just show this thing properly. Yeah, but we want that line kind of helps me visualize the things properly. Anyways, this is the outlier zone. Okay, this part over here where I'm hovering the cursor is the zone of animality. But let me just go to dist plot only. Yeah, this is much more clear to visualize, right? Why is saying that? Okay, hist plot. Okay, let's write hist plot. Let's see what this shows. Okay, nah, I was better with dist plot only. I don't know why they want to remove this thing, but it's just so clear, right? So this is the outlier zone, right, for these values. Now let's do something about this. We have to deal with the outliers. So let me write the next most important thing. So I'm going to deal with, so I'm going to deal with the outliers. So there are many outliers present. We can dive deep with this, but we need to deal with the problem by removing 0.5. So let me write this. We need to remove 0.5 plus 0.5 to basically 1% of the data. All right. So in that way the model is not deprived of raw analysis. right? And then another thing that we need to know is that outliers are situated around the higher prices, right? Outliers are situated along the higher prices, right? You can see it from here, the higher prices out here. So the outliers are situated at the higher prices. Now what is it is useful to try a training model without removing the outliers. So we can always try a training model without removing the outliers, right? And what we can do is, outliers are a great issue for OLS. This is an important thing. Outliers are great issues for OLS. So what we can do, we must discuss this thing as well. We must get rid of this thing as well. So what we can do is that we can declare a variable that will be equal to the 99th percentile of price variable. We can declare a variable will be 99 percentile of the price variable. Got it? Now we have a q thing over here, and q thing we will write data no mv, and we want the price, right? Dot quantile. I hope you know this method. In case you do not know, quantile is basically used to track the percentile format of 0.99 as I have specified over here. Then we can create a new df. Now we will create a new df where what? All the prices must be below the 99 percentile. Right? So let's do one thing. I name it data1. You can name it anything actually. Data no underscore mv, and my bad, I'm going to type price. And now what? Now what? This price data1 should be data no mv, but I'm going to do one small thing. I'm going to call data no underscore mv, and I'm going to say price, but I'm going to include only those values that are less than q. Okay. Now we have essentially removed the top 1% of the price. So now we have removed the top 1% of the price. So what happened over here? You see, here we found that the outliers were for the higher values only, for the higher amount of price. So we did what? We extracted the higher amount of price in the quantity. This is the higher amount of prices benchmark point. And we only want the data that is less than this, less than the top 99%. So we're going like this. See, we had say 100% of the data. Okay. So the top 5%, say it's going in increasing order, it's going in increasing order. So the top 5% out there were the outliers. These were my outliers. So Q is what? Q is basically 99% of this. Right. It's basically top 1%, sorry. So Q is basically the 99%. That is our Q. Right? 99% I think. So if we remove this 1%, if we go for less than Q, then we can remove this 1%. This 1% will get removed, right? So that's what we did. Now if I do data underscore 1 dot describe, and let me just alright. So we managed to deal with that outlier. Now let's move forward. Now probability density function will come to play again. So what we can do now is that we can check the PDF once again, and we can also say, like this I'm not writing right now because let me write sns dot dist plot, and I just didn't mention the name. So now I can see one thing, right? You can see what, that there are still some outliers present, right? So this is what I was going to write. So let me write it now. We will some outliers present. So what to do about them? We can treat the numerical values also for the moment. Let's treat the numerical values as well. Right, let's deal with the numerical values. So what are the numerical values? What are categorical values and what are numerical values? So numerical values are basically the ones that are expressed in terms of a direct mathematical relation. Like for example, price is not really always connected, right? Price is not always going to be like dependent on this and that. There are many external factors that affect price, right? There isn't any technical factor that's always affecting a price. It can be location, can be importing from one place to another. Like for example, this brand belongs to Japan and another brand belongs to France, right? Now in France they have a car that is running at a speed of 200 kilometer per hour, and in Japan they have another one that is at 170 kilometer per hour. But we import this to France. Okay, this normal car will be costing 75 grands maybe, but at the same time this 170 kilometer per hour car would also cost me maybe more than that, maybe 80 rands, because it was imported. Import cost is there. Maybe this one is new, this one is old, new, and this one is old, then it might decrease. So there are some external factors. But when it comes to mileage now, things like mileage, it's completely numerical, it's completely scientific and statistical. It can be calculated numerically. And it's very much necessary to segregate values like that. Wait, I guess I have written wrong spelling. Should be the one. Alright, so here we see the graph, and yeah, there are outliers present. So let's deal with them the very similar way that we did before. data underscore 1 mileage dot quantile 0.99, and then we are going to say data underscore 2 for naming purpose, and we are going to say data underscore 1, and we want data underscore 1 to be fetched, and we want this to be fetched only where mileage, where our body mileage is less than q, right? I feel this plot kind of looks normal, right? This plot looks kinda normal. Okay, now I just tell you why. Kind of have a feeling that this will be normal mileage. Look, that looks normal, right? But you see, when I was looking to the CSV file, I noticed one thing. Okay, I got it from that CSV file only. Did you notice it as well? Wait. Wait. This thing is very strange. Now, open the CSV file, download it from the description, and tell me what should be here. Okay, pause this video and tell me what should be here. Okay, did you guess it? Okay, now resume the video and give a like, share and subscribe right away. Yeah, once you're done with that, then only resume the video. Okay, I hope you have liked, shared and subscribed. No, don't share right away. Just let this course finish. You will automatically have the urge to share this course. Okay, so which one was it? Well, it's engine volume. Look, I'm no mechanical engineer, but I kind of feel it's kind of strange, right? For the engine value values. Have you seen the engine values, engine volume values over here? Can you see the values? Aren't they a bit strange? Very strange. You see, first of all, the most missing values are indicated on 99, which is very awkward. I'll just show you what I mean. You see, probability density function is so useful. It's so damn useful. Now you see this. See the problem. Now if I just do a simple Google search, okay. Oops. Got the formula. Base and board. Yeah, so you can see the values up here. It's definitely not matching. You see, from Google, we get that. Okay, I'm no expert. I found this on Google, so I just wrote it. So it's easier to determine problems with data from an outsider. So we have to cross verify from an outsider who is a field expert. That's your duty as a data scientist. So I just give a call to my friend who is a mechanical engineer and I'll just confirm this. I'll be back in 2 minutes. Okay. Alright, I'm back. So he just confirmed what I was thinking is correct. So let's use our Google knowledge right away. And what I can do is data underscore 3 is equal to data underscore 2 data underscore 2. See, you see in the hierarchy, we first filtered for data 1, then data 2. Like we are reducing the filters. I named this filter hierarchy. This process, I named it the filtering hierarchy pyramid. Ignore my awkward naming conventions. Just get the idea what we are doing, right? Now, following this graph, we realize that we treat engine V as a categorical value. So, this graph is clear reason to treat engine V as categorical value, as there is no direct mathematical approach or logical inference to draw here, right? So store dist plot and see SNS dot dist plot. It underscore 3 engine V. Okay, strange, not very strange, but situation is okay. Fine, why we can just go ahead with this. I'm not exactly happy, but kind of satisfied with this. So finally, random first evaluation would be so good with this, right? So many of you are thinking like that. If you have that feeling, this video is not for you. Okay, this video is for those who are beginning with linear regression, and I want to show them that linear regression being one of those most primer supervised learning models, we need a lot to do manually. A lot has to be done manually. But here you notice one thing. Low end, the prepositional error, it should be at the low end. My bad. Okay, great. So let's do one thing. SNS dot test plot. MV. I'm going to write here. Oh my god, it's such a mess. Okay. Wow. See that the lower end. How did I know it already? Because I had seen the values over here already. I have experience. But if you do not have experience, you don't need any mathematical knowledge. You can just see a variable density function, probability density function. Probability density function mathematically is confusing to many people. But when it comes to visualization, probability density function is the best friend you will ever have in data science field. Now, what I'm going to do? What will I do? What will I do? You know the answer? Comment it down. Alright. Pause the video, think of the answer. And yeah, pause. Okay, play. and I tell you what I will do. So may or may not have guessed this. I will simply remove them. Why? Because we can only use linear regression right now. That's the challenge. I cannot use logistic regression. I cannot use RAVMS. I cannot use clustering. I can't use anything other than this. So, and on top of that, I'm very lazy. So I'll just simply remove them. Yeah, that's the actual reason I'm lazy. Should I write this? Because I'm lazy and who wants to insult yourself on YouTube? Hope you didn't take a screenshot of that while I was writing this. Alright, so we have data underscore 3 and we have okay year year. Make sure of one thing, that when you are into the data frames, right, you're writing these things, you are we're taking care of the cases. Okay, the sentence case, the uppercase, the lowercase, quantile, and it's basically 0.01. Yeah. So now what's happening, since the outliers are at the lower end, we need to do the exact opposite of what we did here. Okay, so we fetched this 100% thing from the back. Right now we are going from the front. We are removing this part. This is the 1%, and we're keeping the 99% from this part. It was from the right of the screen. Now it's from the left of the screen. L, and this was R. So basically, when it is for lower, lower means L, L means left, higher means R, R means right. If you're familiar with binary search, you can find a simple similarity with that, right? Similarity with that algorithm. Yeah. If what I said went past your head, don't worry. It's simply not important. So data underscore 3, we have a year, and I want it to be greater than Q. Why I want it greater than Q? Okay, now at this point, if I not understand this code, why it's greater than Q, then it's probably because your concepts of data frames and Python thing is not very clear. So what you can do right now is that you can go down and take that free Python enlightenment course and meet me back here, follow along like this, and then the things will be like a brisk for you. So now let's view the new result and see if we got what we wanted. So it will be sns dot displot, and I want data underscore 4 sorted as here. Oh yeah, and I made the same mistake again. I don't know why I do this. Okay, I'm hating this warning, but I so want to use this descript right now. It's so convenient. Okay, much better. It's really better now. Now there are a few points that I'm going to write down after I do this thing. So I'm going to clean up some data. So I'm going to write data 4. Wait, this is data underscore 4, right? Yeah, data underscore 4 dot reset, which is function is called reset index. Okay, and drop should be equals to true. Okay, I hope I'm writing the correct thing. Well, if I'm not, this thing will only show me an error or something like that. So remember one thing, when we remove observations, the original indexes are preserved. Now, if we remove observations with indexes 2 and 3, we'll go from 0, 1, 2, 3, 4, 5, 6, dot, 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 dot. Now it's kind of problematic. It's kind of problematic, and the primary reason why logistic regression was introduced. Alright, data got cleaned. Now let's see what's left. Let's see what's left. So for that we need to write data underscore cleaned dot describe include equals to all. Okay, this is making sense. Now we are going to check for OLS assumptions, and this is my favorite part. Just give a markdown and write now. If I search like this, OLS assumptions, and you're gonna see linear regression model, parameters, random sampling observations, ordinary least. So there are 7 classical. This is an article where you find 7 ordinary least squares, blah blah blah. So let me just tell you in brief what OLS is going to be. We are going to do what? My plan is that we are going to compare one value. What OLS assumption does is compares one value against n values, and this one value stays fixed. One value stays fixed. So basically we're trying to find the best match for this value. We are looking for the best match for this value, and we are doing it visually. Okay, we are doing it visually. We are not letting the machine do it. The machine is showing us the thing. We are doing it ourselves. So let's check for the OLS assumptions now. So let's see. I'm going to use some basic techniques. Okay, so let's see if I'm going to take an f variable. Let me name them x1, x2, x3. Okay, we need 3 x's, right? We need 3 comparisons, and I'm going to write plt. So I'm using pipeline. Okay, subplots 1, 3, comma, sorry, 1, 3, comma, into share y equals to. Now the advantage with Python is that the code is so much like English language, very much self-explanatory. Nothing much of explanation is needed here. I love this language for that reason, but at the same time there are some cons with this language as well. As far as machine learning is concerned, there is absolutely no con present over here. It's the best you can get. And let me just write as a, like, for your benefit only, let me just write the share y, share price as y. This is what this share y means. X1 dot, we need to give a scatter plot, data underscore cleaned. I'm going to do it by year. Data underscore cleaned, and do it by price. And in x1 we are going to set underscore title, let's make it price versus year. Now many people write and, which is not the correct thing. x2 dot scatter data underscore cleaned. So we need engine v and price. Yeah. So we need engine volume comma data underscore cleaned price. x2 dot set title price versus engine v. Or maybe we can write volume as well. And x3 dot scattered, the last one, basically data underscore cleaned, and we are going to do it for mileage, and data underscore cleaned, and we're going to do it for price, and ax3 dot set underscore title price versus mileage, and plt dot show. Alright, so look at the three beautiful graphs we have over here, looking very cool, right? It's looking so great. Such a good comparison method. Probability density function is OP. Let's go ahead. And now I'm going to write from the subplots. We can easily determine that price is exponentially distributed. Now from these subplots, we can easily determine that these PDFs are for price is exponentially distributed. So now tell me, when I use the word exponential, my bad, this graph, and this graph, aren't they logarithmic graphs? Yes or no? If any BTech student is watching this and you didn't really figure it out as a logarithmic graph, your career is over before it started. Sorry to say that. Anyways. Not if you're a newbie, ignore it then. It's a simple log transformation that we're going to do. So let's say SNS dot distplot underscore cleaned price. Alright, logarithmic transformation completed with success. Now we need to relax the assumptions. So you can take some relaxation now because we are coming close to being done. So we need to relax the assumptions. So let's transform price with a log transformation. And log price equals to np dot log. So I'm using numpy. Numpy has a log function over there. This is how we add data to an existing data frame. Simply write log underscore simply add name. You can write anything. Now over here you could have simply written anything, okay, any name, but just to make things simpler I am keeping these two things same. This is the same concept that I've used in object-oriented programming. Okay, done. Much more cleaned of a value. Now what we are going to do? Now we are going to revisit the scatter plots that we had. So basically what we had formerly, we are going to get that same thing. This exact thing I'm going to copy and I'm going to paste. But instead of price, I want log price. I want log price. Let's replace price with log price in all the cases. And let's, set the titles. Oh my god. Now this is so much better. But now see, since we already have the log price thing and we are going to use the log price thing only, right? So why don't we remove the normal price variable? Now we are going to check for multicollinearity. Alright, so we are going to find multiple collinear data values that are present over here. Let me write it with a heading only because this is important. Multicollinearity. Power of NumPy and pandas. We have it. Only the column values. Alright, let's get rolled. Now the problem is that sklearn it does not have a built-in way to check for multicollinearity. So it is she's what do I say? We have to deal with this. So in order to do that, I've come up with a solution. Not I, some smart people have come up with the solution, and I'm going to copy their solution. This was an open source problem till a certain time, till this was invented. The small extensions. Now our work is a bit more easier. I'm gonna give you the links and other things out here in the description. Okay, full documentation for that article where this method is discussed in detail. I will give that in the final edition of this Jupyter notebook that I am going to upload. Okay, in my GitHub there are many other projects out there. In my GitHub you can check them over there. Variance inflation factor. And now to make this easy as possible, we need to declare a variable where we put all the features. Now we need to declare a variable where we all the features. Which features are we talking about? This is going to do with mileage, we are going to do it with year, and the other one was engine volume, engine B. Now for the variance inflation factors to be contained, we will need a new data frame. We need a new data frame all the VIFs. For the VIF, I'm going to make a variable which is again going to name VIF pd.data frame. Now data frame is in camel case. Now VAF features. So we need the variables, and from the variables we only need columns. Now let's explore the VAF. Simply type VAF. Great, we have the features. Now what we are going to do, we are going to create dummy variables. Okay, so we are close to the end, so we are going to create dummy variables. Alright, so now we are going to create dummy variables. But we need to drop the dummies once multicollinearity has been dealt with. Alright, so why we want to do that? Because we do not need the dummy variables, because we are not going to use logistic regression. Dummies basically refer to what? But you will get it. Data underscore no underscore okay, semantic unit is not defined. Okay, I have not defined. We're going to drop here and we're going to write access equal to 1. And I guess I missed this. Yeah. So we are done. So let's see data with dummies dot head. I want the first 10 values as usual. Okay, so you can see these dummies out here, 1 and 0. These things we need in logistic regression, but here we just need it for calculating the multicollinearity. So to rearrange them, so now we need to arrange the values, and for that we can just simply write data underscore with dummies dot columns dot values. Got this. Awesome. Now we need to parameterize the contents. Parameterizing the contents. For that we need columns. And for that we're going to manually write like this: log underscore price mileage engine V brand underscore BMW you can just copy it. Engine type gas, engine type petrol, engine type registration. Yes. Yep. Done. So now we need to implement the reordering. I'm going to implement the reordering. Data preprocessed equals to data with dummies columns head and the first and else. Bingo. Done, 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 done. Now ultimately we move to our linear regression model. We ultimately move to a linear regression model. So first what we will do, declare the inputs and targets. And we know dependent variables is log price, targets equals to data underscore pre-processed log underscore price. Now remember, the inputs are simply the dependent variable. So they can be dropped. Like for example, what I'm trying to say is, this is a very important thing, right? So if x is dependent, we need to calculate y. So in the data frame that we have, this x thing is not needed, because on the basis of this thing I want to calculate this, and the other way around. So you can just simply drop it. preprocessed drop log price x is equal to 1. Okay, and I'm making these mistakes too much these days. Now we need to do what? We need to select the data. Let's select the data. Now we need to import the scaling model. For that, from sklearn dot preprocessing import standard scalar. Now we need to create a scalar object. So for that, scalar equals to standard scalar. Now fit the input. Notice we didn't directly fit the method, so we use standard scalar. It's because we had a logarithmic graph and we knew the values. Right, so let's fit them. So we have a standard scalar object. Now we need to transform this. Or rather, input scaled will be the name. Scalar dot transform trying to split from sklearn dot model import train test split xtrain x test. I want to separate them as 80% 20%. Okay, 80% for training, okay, testing 20% and the rest for training, 80% for training. So let's do it like that. Xy train and y test equals to train test split inputs underscore scaled comma targets comma test underscore size equals to 0.2, and we need a random state of 365. Now let's see what we are doing. Why we are splitting the test. Input scaled, right? There's nothing to be here. We had the scaled inputs. We are attacking the targets that we had, right? Log process, log price, random state. Let's go ahead. Let's go ahead. Train test split done. Now let's create the regressions. Only the regression. So let's name it reg. I'm just gonna call linear regression. Fit the model. So you're gonna write reg dot fit x underscore train comma y underscore train. It's done. Now we just compare the targets and y at values. So let's set plt dot scatter y trend comma y hat. And what is this y hat? Y hat is basically reg dot predict. What are we going to predict over here? Basically x trend. Now plt dot x label, it targets y trend. Size equal to, let's say, 18. plt dot y label which are predictions, which is what we call y hat. Size will be 18. plt dot xlim 6 comma 13. plt dot ylim 6 comma 13. And finally plt dot show. Now just see, and voila, look, except a few data sets scattered here and there, we have such a constant line, constant scatter plot, which is really great, which is really great. Now if I write, I create a dist plot for y underscore train comma and subtract y underscore hat from this. Let me just name it a plt.title title residuals. So this is the probability function of the residual dataset, the ones that are the outlying ones, the outliers, these ones that are scattered away. I need to see how much important they are, how much of effect they are having on a dataset. Now remember, this is basically model. I mean, there were probably a lot of factors that we have overlooked or something. We need to remove them. Yeah, we have this. Now we need to find the r squared value of the model. Which means basically we're trying to find all these points, all the values for these points touching the r line, regression line. Okay, for that we will write rec dot score x string comma y underscore trend. Now voila, which is 74.5, which is too much, kind of great if we consider we only used linear regression. We have the intercept of this, we have to find the coefficient. This is the coefficient. Now we can create a regression summary. So let's create a regression summary for now. So we will name it regreg underscore summary equals to pd dot data frame inputs dot columns dot values columns equals to features okay, here we go. Now we need to check the different categories in the brand variable. Now we need to check and filter the different categories for the brand variable. And in this way we actually see that brand is the benchmark value. Now It's predicted. X test. So the scatter plot, plt dot scatter y underscore test, comma y underscore hat underscore test, comma ALPHA equals 0.2, plt dot x label, targets y underscore test, size equals to 18, plt dot y label, predictions y underscore hat, size equal to 18, dot xlim. We have 6 comma 13, value will also 6 comma 13. All right. Now let's manually check these predictions. All right. Now we know we can also include the test targets so that we can manually compare them. Okay, now this is not good. The above results show that indexing, but this is not good. Not good at all. Let's do one thing. Let's drop the indexes. Let's use the magical reset command. Okay, this makes more sense. So now let's better finally all of a sudden. Now let's again calculate the residual difference. So for that we have df Alright, now we have, let's calculate the percentage also. Percentage of the differences. Yeah, that way. So we are going to use numpy again. So we're going to use numpy's absolute method. So we're going to write df pf residual divided by df underscore pf of target basic class 10 or 9 mathematics, and we're going to into 100. Here we go. Let's see df underscore pf. Okay, we have difference percentages, and we're going to write df underscore pf dot describe satisfactory values. So let's see, let's use okay p dot options dot display dot max underscore rows 999. I'm gonna write pd dot set underscore option dot float format, and I'm going to use a lambda function where I'm going to do the conversion thing. So it will be like let's see, percentage dot 2f. So I'm going to show the values up to only two decimal places, modulus of x, and df underscore pf dot sort values, and I'm going to sort them by, let's see, difference is percentage. All right, here you go. Here you go. We have our values. We have our beautiful target presentation. I don't know if I can write dot head and for the first 15 values. Yeah, awesome. So our final presentation is completed with our car evolution project. I guess it was a lot of fun. I'm going to add in a lot more comments in this file. Comments for everything that I've said or told, and it will be available as if in my GitHub. You'll get the link in the description along with the blogs that are important, all the necessary links, all the necessary places to follow. Just go to the description box. And yeah, of course, if you want to get a deep dive into machine learning, just go ahead and join our course. It's waiting for you, and I'll see you in the next video. Till then, subscribe to our channel and stay tuned.